Welcome. We start the fourth module of our course, that is design of separation processes. In the previous two modules, that is the input output structure of the flow sheet and the recycle structure of the flow sheet, we saw as how we can fix the total mass and energy balance of the process and also go for the reactor design. The next stage in the design of the process is the design of separation processes. The effluent that will come out of the reactor will have several components, several products, byproducts, unreacted reactants, and all of these need to be carefully separated before purification of the main product. So, we shall see as what are the guidelines that govern the design of a separation process. Separation and purification of the products is an important aspect of the design of the process. The stream emerging from the reactor comprises of main products that I just said. The separation of most of reaction mixtures to their constituent species is not spontaneous, and therefore, the separation occurs at the expenditure of energy or use of other mechanical forces. When the feed mixture is homogeneous or a single phase solution, then a second immiscible phase has to be developed or added, and the second phase is generated by either addition of a mass separating agent or energy separating agent. Now, the most common operations used in chemical industry are absorption and distillation for separation of the processes. Okay. In the NPTEL course of mass transfer, you have learnt the basic principles of these processes in great depth. So, I will not go for repetition of it, but we shall see these two processes from economics point of view. Okay. That is the additional feature of this particular course of NPTEL. In addition to absorption and distillation, we also have azeotropic or extractive distillation, stripping, extraction, crystallization as the techniques for separation of the components of the reactor effluent. More recently, use of microporous and non-porous membranes as semi-permeable barriers in separation of the component mixtures has received considerable attention. The separation techniques that fall under this category are microfiltration, ultrafiltration, nanofiltration, osmosis, reverse osmosis, gas separation and pervaporation. Now, these separation processes have merit that these are less energy intensive as compared to distillation and absorption. In case of absorption, the particular component in the gaseous mixture is absorbed in the solvent. However, we need further distillation to recover this particular component and recycle of the solvent. So, although absorption itself could be absorption on its own could be less energy intensive, but coupled with the distillation for the recovery of the solute, it becomes energy intensive process. The advantage of these membrane processes is that they are far less energy intensive as compared to absorption and distillation. However, there are certain limitations of their own that we shall discuss later on in this lecture. Removal of certain components may also be achieved using solid mass separating agents. Now, the separation processes that fall in this category are adsorption, chromatography and ion exchange resin. The use of external force field can also be used sometimes to provide the separation driving force between dissimilar molecules and ions. For example, the usual method of separation of solid particles from a reaction mixture is that of settling. Okay. However, if the particles are very small, then their terminal settling velocity is very small, and then it takes very long time for separation of these particles, as you have already seen in the course of fluid mechanics and unit operations. In some cases, they even form stable emulsion, where the forces on the particles are perfectly balanced and it remains suspended in the solution. In such cases, we have to apply additional force. It could be either mechanical force such as centrifugation, or it could be electrical force as in case of electrolysis or electrophoresis or electrostatic precipitation. So, these are some of the additional techniques for separation of the components of the reactor effluent. As far as heterogeneous mixtures are concerned, it is more practical to use mechanical processes based on gravity, centrifugal force, pressure reduction or electric magnetic field to separate the phases. Okay. Methods used for separation of heterogeneous mixtures include settling and sedimentation, which I just mentioned. However, we need a certain particle size or the density difference between solid and fluid to achieve effective settling and sedimentation. Then there is process of flotation, where you generate a froth, like generate bubbles in the solution of the solid mixture and solvent, and certain particles from the solid mixture attached to the bubble surface, that we are going to see in greater details later in this course, in this lecture. Okay. Then centrifugation, which I just mentioned, use of centrifugal force, then drying, which is basically for removal of the moisture, evaporation and filtration. Now, filtration is another cousin of membrane separation, but this filtration is completely mechanical, okay, where the particles are separated by only size exclusion. Okay. Evaluation and selection of separation process for a particular mixture depends on the overall economics of the process. Okay. We shall see the criteria for selection of the process very shortly. However, economics comes into picture. There could be several alternatives for separation of the same reaction mixture. However, we have to assess based on the throughput of the volume that is to be processed, the concentration that is there in the reactant or effluent of different components. Based on several factors, we have to select the best possible process that will give most effective as well as economic operations in terms of both fixed and operating cost. The other measures for evaluation of the effect of separation operation are recovery, percentage of the key products obtained from the feed mixture, and secondly the product purity. Same purity may not be obtained from different processes. So, depending on the cost of the component that is going to be recovered against purity, we have to select certain process. In some cases, we may go for energy intensive process for separation or for the recovery of that particular product, because it gives high purity and the cost that purified product draws is worth the or which offsets the cost of separation. We shall see the selection of a suitable separation process. What criteria we have to use for selection of the process to separate the same reactor effluent. The important factors to be considered in making selection of the suitable separation process for a particular application are: first, the exploitable property difference, whether it is physical property or chemical property, then the feed and product condition, which I just mentioned, that what is the volume of the feed, what is the phase of the feed, and what are the number of products that are available in that are present in the reactor effluent, then the characteristics of the separation process. Other important feed conditions are the flow rate and composition that I just mentioned, and particularly the key components that are to be recovered and separated. Now, one obvious feature of the whole separation process is that how concentrated is the reaction mixture to be separated. Okay. The more dilute the key components in the reaction mixture, the greater the cost of separation. Okay. That is obvious, because you have to treat a very large amount of volume for recovery of very small amount of product. So, the cost of operation increases with the volume that is being treated. However, the cost of product even with 99.999% recovery is much lesser. Then another criteria for selection of the process is the exploitable property difference. The designer must also have some understanding of the general regions of applicability of the process. Achievement of very pure products either requires large differences in certain properties between components to be separated, or requires large number of stages for separation. You have already seen these things in the course of mass transfer in this NPTEL. Okay. You must have seen that as the number of stages increases, okay, in a distillation column, the product purity increases. Okay. However, to achieve there is again a trade off between the reflux ratio and the number of stages. If you have greater reflux, then you have lesser number of stages, but the amount of product removal is less. Also, the volume that is under treatment at a certain time increases, so the column size diameter increases. but the number of plates decrease. So, there is a trade off, okay, that we have to see. Generally, when separation process is well understood, it can be readily designed using a mathematical model and scaled up to handle the industrial flow rates. Now, elaborate mathematical models are available for processes which are in operation in chemical industry for last 1 century, that is absorption, then liquid extraction, distillation. There are certain professional softwares which give very elaborate design of these particular processes. So, once the mechanics of the process is understood, it is very easy to develop a mathematical model for that particular process and then scale up according to the simulation results using the mathematical model. Some separation process may require a pilot plant testing before final design with some assurance of the operational success. Operations based on barrier separation are more expensive to stage than those based on creation or addition of a second phase. For example, membrane modules are difficult to stage as compared to the distillation or absorption, okay, which is creation of addition of second phase. Then some separation processes are limited to maximum size, hence use of parallel units is necessary. If the throughput is very large, then the size of one single unit treating the entire throughput becomes impractically large. In that case, you have to go for several parallel units. In some cases, there is problem of fouling, there is problem of clogging, some operational problems. Therefore, it is always better to put some equipment under standby, which means that when one equipment is under repair or maintenance, the second unit can operate and take the load of overall treatment. The choice of single or parallel units has an important effect on the economics of the separation processes. Obviously, there is a trade off here. If you split the total feed to be treated into two parts, then you will have two equipments of moderate size, but the individual cost of operation goes down. Okay. So, two distillation columns, okay, the fixed cost will be higher because you are having two units, separate units. There is always an economy of scale up. If you have one big single unit, it will definitely cost lesser than two single units of the same total capacity. Doubling of the capacity of a single unit will increase the capital investment by 50%, while use of parallel units to handle the doubling in capacity will require an additional investment of 100%. That is what is obvious from the discussion that we just had. Then let us see what are the property differences associated with various separation processes. As I said that we have to identify the exploitable property difference of different components that are present in the reaction mixture so as to achieve the separation. One simple separation, like for example separation by sedimentation, there the difference is of density. So, density is the property that is exploited. But let us see we have seen so many operations of separation. Okay. What operation is suitable under what property difference available? Okay. Now, the easiest or the most obvious property difference is the vapor pressure. Many processes are liquid phase processes. Therefore, vapor pressure of the liquid is a very handy tool or handy property for design of the separation processes. The separation process, which is based on difference of vapor pressures of different components in the reaction mixture, are distillation, absorption, stripping, drying and evaporation. Solubility is another property, and crystallization or leaching processes make use of this property for the design. Okay, differences in solubility of different components in a particular solvent. So, that is a basis for design of crystallization or leaching process. Then the distribution coefficient. Okay. When a particular component, when a particular reaction mixture is contacted with a solvent, then not all of the components that are initially present in the reaction mixture have equal affinity or solubility in the solvent which is contacted. So, some components get selectively solubilized or diffused to the second phase that is added, that is a solvent, and this helps us in achieving some separation between the components. So, the distribution coefficient or partitioning coefficient is the basis for design of process of solvent extraction and adsorption. Then the exchange equilibrium. This is a property for ion exchange resin or chromatography. Then the surface activity, that is used for froth flotation, like there is some surface activity, some attractive forces between certain solid particles and the bubble surface, which is of hydrophobic character. So, in froth flotation bubbles are generated and particles from the when you have a solid mixture, then particles of a certain component get attached to the bubble due to the surface activity. That is the property for design of froth flotation process. Then the molecular geometry, that is for membrane and dialysis. Okay. Then the electric field for precipitation. Then the particle size is a property for filtration, screening, settling and sedimentation process. Then particle size and density together are the properties for the design of centrifugation or classification, thickening, decantation or scrubbing processes. Let us see certain general guidelines for selection of a separation process. I would like to mention that these are very broad guidelines. These are not applicable like hard and fast for each and every process, but these guidelines give us a general view or like thumb rules for selection of a separation process. So, let us first take the process of distillation, which is one of the most common processes used in chemical industry. Now, in this case, the feed condition of the reaction mixture has to be liquid or some mixture of vapor, okay, or it could be even be complete vapor. Then the mass fraction of the key components has to be between 10 to 95%. It cannot be too dilute, below 10%. You have to handle a very large amount of liquid. As I mentioned at the beginning of the lecture, distillation is an energy intensive operation because you have to boil a large amount of liquid. However, people still go for distillation because of the flexibility of product purity that can be obtained from the distillation, and also the know-how that is already established for distillation column design. Okay. For these two things, people would like to go, the designer would like to go for operation of distillation for separation of reaction mixture. The normal feed capacity is between 1 to 100 kg per second. Then advantage is simple flow sheet that I just mentioned. It is a well established process, lot of data is available. So, design of a very efficient column is easy. You can even energy integrate these columns, as we shall see subsequently, that if you have a series of columns, then you can alter the pressures in these columns, so that the vapor from one column can drive the reboiler of the second column. That can be achieved by adjusting the pressure, that is energy integration within a distillation sequence. So, distillation is a very well established science, okay, and that is a major advantage of it. Then low capital investment, easily scalable, okay, you can go for large scale. The limitation, however, is that of need of adequate volatility and thermal stability of the component. Okay. If the volatility is very close, then you will end up with very large number of plates, very tall column, that will give you enormous capital investment. And then if the components are thermally unstable, then you will have to control the temperature very carefully. Another problem with the distillation is when extremes of temperature and pressures are encountered. For example, if the vapors that are in the system, like at the reboiler, at the condenser, the vapors at the condenser, if they condense at temperature lesser than, let us say 20 degrees centigrade, which is a typical entry temperature of cooling water, then you will have to give a special utility for that condenser. For example, let us say chilled water. If the condensing temperature is even below, let us say below 5 degrees centigrade or below even 0 degrees centigrade, then you will have to go for refrigeration. So, typically for temperatures lesser than minus 40 degrees or greater than 250 degrees, the cost of added refrigeration or heating involved escalates rapidly, and then the operating cost also goes up. Same thing holds for reboiler also. The most common utility for reboiler is steam, that is either medium pressure or high pressure steam, but that is up to 250 degrees. If the boiling point of your reaction mixture, the bottoms, of the distillation is greater than 250 degrees, then you have to go for some special utilities such as furnace or Doutham liquid, and that increases the cost. You can have pressure variation, like for example, if the boiling point of the distillation column bottoms is greater than 300 degrees, then you can apply a vacuum to lower it so that you can still use steam, but at the same time you have to see that how the condensation temperature of the vapor also decreases with pressure. It should not go below 20 degrees, so that you will have to use refrigeration. So, this is all a big trade off, but typically if you see the typical temperature range of a distillation column, it is between -40 to 250 degrees centigrade, above which the operating cost escalates the total cost of operation. Then there is azeotropic distillation. Azeotropic distillation by definition is to separate the components which have same volatility. Okay. Like for example, ethanol water mixture achieves azeotropic composition after about 87% mole percent of ethanol. Then at that time the relative volatility becomes 1 and no more distillation can be applicable. Okay. In that case, we have to go for azeotropic distillation. Now, the feed condition for azeotropic distillation has to be either liquid or vapor, which is dictated by the azeotropic composition. The separating agent is a liquid entrainer and plus heat transfer. So, you have to add an entrainer which binds to, which forms a temporary complex with one of the components, and then that complex has volatility greater than 1 with the other component, and then you can achieve the separation, and then later on that particular complex is broken to achieve to recover the entrainer, which is recycled. But addition of a third component increases the cost. The azeotropic distillation itself is much complex operation than mere distillation. You have to be very careful while designing the column. The degrees of freedom are less, and therefore the cost rises. Okay. The feed capacity is typically 1 to 60 kg per second. Distillation may also be unsuitable when undesirable side reactions occur at column temperature. This can result in product loss and significant formation of the byproducts. Then there is the operation of absorption. This is another widely used operation in chemical industry, and it is also used as an alternative to distillation for separation of solute from gas stream. The gas mixture is contacted with liquid solvent which preferentially absorbs one or more components from gas stream. The absorption factor, which is L by mg. L is the molar flow rate of liquid, m is the slope of the equilibrium line, equilibrium curve, and g is the molar flow rate of gas. The absorption factor L by mg for relatively dilute components in the gas phase determines as how readily that component is absorbed. When absorption factor is large, absorptivity will be increased. However, you will have very large amount of liquid which is rather dilute, and then the recovery of the solute from that liquid becomes uneconomical. Okay. We have a separate module for absorption column design, that is the economic decision making during design of an absorption column. So, I do not elaborate this thing further. We have a separate module for it of about 4 to 5 lectures. So, I suggest that you watch that module very carefully to see as how economics and the engineering can be coupled for design of a distillation column. The optimum value of absorption factor is 1.4. Now, how it is explained in the module of economic decision making of absorption column. So, I suggest that you watch that module to get answer to that question, why 1.4 is the optimum value for absorption factor. Then there is process of stripping. Stripping is exactly opposite of absorption. Once a solute is absorbed in the solvent, it is necessary to separate the solute from the absorbent in a stripping operation and recycle back the solvent. The stripping factor is exactly opposite mg by L, which is of significance, and well, it should have a value between 1 and 2, optimum again 1.4 for dilute mixtures. Okay. Stripping could be achieved even by steam, that you pass superheated steam through the solution that contains solute and solvent, and the steam takes off the relatively volatile solutes, then but in that case the solute has to be immiscible with the steam, and then you condense the whole vapors to get the solute. Then it forms two phases, and then the liquid the water part can be recycled for generation of steam further, and solute can be recovered. Then the process of extraction. This is often used to separate azeotropes and components with overlapping boiling points. Extraction process requires addition of a solvent in which one or more components in the mixture are soluble. Again, the principles of this operation you are already learning in mass transfer course. So, we will not deal with the basic principles of this process. Okay. Now, again here there is a trade off. We have to add a solvent. Then there are two things. First is the distribution coefficient and the selectivity. You have, let us say, more than one solutes, then you should have a higher partition coefficient of the desired solute, and it should be also, your solvent should also be selective, that it should pick up selectively one solute, leaving apart the others. Now, this advantage of this process is that it offers great energy saving. Process can be operated at low to moderate temperatures for recovery of thermally sensitive products. Then requirement of solvent increases the complexity of the process. You have to very carefully study the liquid properties. It has to be heterogeneous. Okay, the ternary diagrams that we have learnt in mass transfer course help you guide selection of a suitable solvent. The recent advance in this field is that of supercritical extraction using supercritical fluids. Now, supercritical fluids have greater solubility or selectivity, so that they increase the extent of separation that can be achieved. Okay. However, extraction operation itself will not give you the desired product. It has to be coupled with a distillation operation. The output or the extract that is from the extraction product contains solute and solvent, which has to be separated, and then the most common operation is distillation. However, the subsidiary distillation operation, if you have to make it less in cost intensive, then you have to select a solvent which has a very high relative volatility with respect to the solute, so that you can achieve separation in very small number of plates. The solvent which you are going to use should also have less boiling point, and it should be less viscous, and so on and so forth. So, well, these things you have already learnt in mass transfer course, that what are the desired properties of the solvent for a particular extraction process. Primary disadvantage of supercritical extraction, however, is that the extractor must be maintained at very high pressure, sufficient to keep the solvent in the supercritical state, and therefore, the capital and operating cost are high for this kind of extraction. So, this point has to be noted when we talk of advantage of supercritical solvents. Then comes the operation of crystallization. This is about recovering of the dissolved material in the solution in solid form by precipitation upon cooling or removal of solvent or addition of precipitating agents. The most common method of achieving crystallization is that you dissolve the solids in a suitable solvent at high temperature, because solubility usually increases with temperature, and then cool that solution, so that at lower temperatures the solution becomes supersaturated, and then the precipitation occurs. However, the pure component, although impure solids dissolve in the solvent, only the pure component precipitates out, and all the impurities are retained in the solution. The design of the crystallizer is based on the knowledge of phase equilibria, solubility, rates and amount of nuclei that are generated, and the rate of crystal growth. You have already learnt the MSMPR model, mixed suspension mixed product remover model, in topic of crystallization, which will be covered in mass transfer course. Okay. MSMPR model uses the delta L law, that it assumes that the crystal is growing equally from all sides. Then you have a trade off between delta G, and then you get the predominant particle sizes 3 times the retention time. So, all these things you have already learned. Okay. But now we shall see how crystallization is useful for treatment of very large amount of reactor effluent that comes out. For this operation, pilot plant design is normally required to establish the critical design parameters. Both batch and continuous crystallizers are available. Earlier, before development of the adsorption process for separation of xylenes, crystallization was a major operation for separation of xylenes. Like orthometa paraxylene, they have very close boiling point. Therefore, separation of these xylenes through distillation is highly energy intensive and cost intensive. But however, if you see the solidification temperatures, these were quite different, and therefore the xylenes were separated by crystallization and not by boiling. Okay. So that you cool down the temperature at about minus 40 degrees, the ortho xylene separates out, and then meta and para further can be separated by lowering of temperature. So crystallization is a very common operation that is used in industry. Okay. Various types of crystallizers are available, and however, before you choose a particular crystallizer for a particular operation, pilot plant testing is necessary. Then comes the topic of membrane separation, which is one of the most popular modern day process for separations of different reaction mixture. As I already told you that membranes overcome a major drawback of the conventional operations of absorption and distillation in that they are very less energy intensive. Okay, they only have a barrier in the form of membrane, and separation occurs at no high energy cost except for pervaporation that we shall see later. Okay. These types of separations are accompanied with use of specifically prepared membranes that selectively permit one or more components to pass through the membrane while retarding passage of others. The stream passing through the membrane is referred as permeate, while the stream that is retained by the membrane is retentate. The driving force for separation is the difference of pressure that is applied at on the two ends, two sides of the membrane. Membrane can separate at molecular level or very small particle level, and large number of separations are now available using membranes. Membrane separation except pervaporation, where a component dissolves at one side of the membrane and then diffuses and then evaporates on the other side. Okay, that is what pervaporation, permeation, evaporation. So pervaporation, that is only a slightly energy intensive operation, because there is a phase change that is occurring across the membrane. At one side the component is dissolving in liquid state, and on the other side is evaporating. So that the energy of evaporation is absorbed from the liquid, that is on the other side. So you have to continuously keep that liquid at a certain temperature. Except that operation, the membrane separations are less energy intensive. Now I will give you some common membranes processes, okay, and the size classification. For example, the microfiltration. Microfiltration works on size exclusion. The operating mechanism is size exclusion, and the pore or intermolecular size is something like 5 into 10 to power 8, 5 into 10 to power minus 8 or to 5 into 10 to power minus 6 meters. Okay. Then ultrafiltration. This works again on size exclusion, and here the pore size is even lesser, 2 into 10 to power minus 9 to 5 into 10 to power minus 9 meters. Then the nanofiltration, this also works on size exclusion, that is the pore size is lesser than 2 into 10 to power minus 9 meters. Then reverse osmosis, reverse osmosis is considered as a potential process for desalination of seawater so as to make it potable. Okay. Here the mechanism is solution diffusion, which means one of the components selectively gets dissolved in the membrane at one end, it diffuses to the other side and then desorbs. Okay. So here the pore size is lesser than 1 into 10 to power minus 9 meter. Then there is pervaporation. Here there is solution on one side, then diffusion on the other side, and then evaporation. You have to maintain lesser pressure at the permeate end, so that the component evaporates, and here also you have the pore size less than 1 into 10 to power minus 9 meters. Okay. So that is the typical size classification of the membranes. Although membranes have several positive points to their credit. There are also some limitations. For example, the product purity. Two pure products as distillation may not be obtained. Distillation column can be designed to get 99% or 99.9 or 99.99% pure product, but that kind of design may not be available with the membrane unless and until it is extremely selective. That is thing. It is also difficult to stage membrane modules. Okay. They also cannot operate at high temperature, as the polymer may swell and cause damage to the membrane. Then another point is that of the purity of the liquid that is being treated. Any solid impurity in that liquid can rupture the membrane and can hamper the complete operation. Okay. Membranes have also been used in many electrochemical processes. For example, the caustic soda manufacture is nowadays solely using membrane cells, which allow passage of certain ions, only cations but not anions, and they give very high electrical efficiency. But again, the brine that is suitable for treatment in case with membrane cells has to be very pure. Like for example, any solid impurity has to be reduced to ppb level, parts per billion, and then the cost of this purification adds to the total operating cost, although means it is a trade off. You are saving money due to higher electrical efficiency, but at the same time you have to go for more stringent conditions for your feed quality, and that to meet that stringent condition you have to go for additional separation processes, which could be expensive. So, that is all about the membranes. Then comes the operation of adsorption. It is as old, if not as old, but it is as conventional as absorption. Now, here the basis of adsorptive separation adsorptive process is that one or more components from the mixture get adsorbed on the suitable adsorbent, and the regeneration of the loaded adsorbent is possible through either a thermal or pressure swing. Now, these are very widely used technique, okay, in separation of many products. For example, air splitting. Now, pressure swing adsorption PSA is one of the very popular processes used in process industry. Okay. In pressure swing adsorption, you use zeolites with very controlled pore size, and then air separation is achieved, that you pass oxygen and nitrogen and then apply high pressure, and then the smaller molecule that diffuses inside the zeolite, the pores of zeolite, and then gets adsorbed. Okay. And then the relatively pure other component nitrogen is left, that is taken out. Now, you have an adsorbent which is loaded with adsorbate, that is oxygen, and then it is subjected to the pressure swing, that is the total pressure is reduced so as to desorb the adsorbed component. Okay. Now, the physical basis for desorption process is that the forces that bind adsorbate to the adsorbent are weaker than the forces that bind atoms together. Okay. That is a very simple principle. Okay. Adsorption is very commonly used. Like for example, our domestic water purifiers use activated carbon, activated charcoal as adsorbent for separation of organic impurities. Okay. We in the northeast we have lot of iron in the iron dissolved in water, and that can also be separated using a suitable adsorbent resin. So, adsorption is a very common operation which is used all over industry as well as in several domestic gadgets. The major problem with adsorption was that when you use a thermal swing, for example, adsorption is bond formation, so it releases energy, and therefore, if you have to desorb the adsorbed product, then you have to heat it so that the product gets desorbed. But this thermal swing can cause sintering of the particles. If you are using the same adsorbent bed over again, then successive operation can cause reduction in the adsorbent capacity. Secondly, the adsorbent is the mass separating agent, solid phase, and hence its movement from one location to other is difficult. Therefore, recovery of the adsorbed material is achieved by subjecting the adsorbent to either thermal swing, as I just mentioned, or pressure swing, that pressure swing adsorption as a bed itself. Okay. So, you cannot separate it, and then transportation is difficult. In some cases, like when for separation of methane, methane and ethane from the hydrocarbon gases, they used to have a convective loop like air convection. They used to have a counter current operation with adsorbent passing from top to bottom and gas hydrocarbon mixture passing from bottom to top, and then after the adsorbent comes down, it is lifted back to the top of the tower in air conveyor like pneumatic conveying, so that the sintering, the attrition and sintering effect is lowered. Ion exchange is a cousin of adsorption. Ion exchange is also a similar process as adsorption in that solid particles are used and regeneration is necessary. However, in this case a chemical reaction is involved. Example is that of softening of water, okay, when especially the boiler fed water, which is used for generation of steam, where in this case a solid organic polymer in its sodium or H form, the hydrogen form, exchanges calcium and magnesium ions which are likely to precipitate, which is called hardness of water from water. The ion exchange column after exhaustion can be regenerated by treatment with concentrated sodium salt solution. Okay. Now, these ion exchange resins are quite widely used for making boiler fed water, the demineralized water as they call. These ion exchange resins are also used for preparation of brine for caustic soda industry that I just mentioned. So, ion exchange is also a very common operation for separation of the reaction mixture. And then comes the process of flotation. I have already discussed this briefly before. It is basically the process of separation of specific solid-solid mixture using gas bubbles. The gas bubbles are generated in the liquid and become attached to selected solid particles which are lifted to the top, allowing them to rise to the liquid surface. Then the solid particles are removed from the surface by an overflow weir or a mechanical scraper. The separation of particles is dependent on the surface properties which govern the attachment of solid particles to the bubble surface. Now, many times coal is purified using this kind of technique. For separation of coal particles from impurities can be achieved by what is known as a froth flotation. There are several factors that govern the efficacy of froth flotation, that there are several surfactants are added, the pH has to be controlled very properly so as to achieve as maximum separation as possible. And then finally, we shall see the centrifugation and filtration. Centrifugation is for separation of either solid particles, or it can also be used for separation of some heterogeneous liquid mixture. Centrifugation is the separation of particles in the fluid through application of centrifugal force field. The liquid is put in certain vials and or containers, and it is rotated at very high RPM, 5000, 6000 RPM, and then the particles get thrown out because of higher density. Okay. This is usually applied when the gravity separation of the heterogeneous mixture is too slow because of the close densities of the particles and the fluid. So, centrifugation is thus used to break stable emulsion. Then the process of filtration. Filtration, again it is a sort of membrane process, but it is not for as small particles as being used for membrane. These are for like macroscopic particles. In this mode of separation, the solid particles in liquid or gas are removed by passing of the mixture through a porous medium that retains solid particles and passes the fluid. The filtration occurs by either cake filtration, in which the particles are retained on the surface of the filter medium, or depth filtration, in which the particles are retained within the filter medium. The cake formed on the filter medium as the filtration proceeds, okay, it offers additional resistance to the fluid flow. Therefore, the pressure drop across the total filter, it could be a stacked filter with stacked pieces of the filter. It could be the filter medium could be a cloth of natural or artificial fiber, or it could be even metal, and these filter media are basically enclosed in metal boundaries, okay, or metal frames, and then these are stacked one after another to achieve as high separation as possible. But as the filtration proceeds, the formation of cake increases the pressure drop across the filter, so that has to be carefully monitored. And then as the cake formation increases, the amount of the flow rate of the filtrate decreases. Okay, so one has to carefully study that that this particular portion will be covered in the course of unit operations, the filtration, as how you can obtain plots of cumulative volume collected versus time, and then from that plot you can calculate the resistance of the cake. It could be either compressible or incompressible cake. Okay. So, all those things, the basic principles you are going to see in other NPTEL courses. Here we shall see only the economic aspects. So, when you are trying to separate these macroscopic particles, you have to see that the cake formation does not exceed a certain thickness. Okay. So, you have to continuously scrap the cake from the filtered surface, or if it is depth filtration, then once the pressure drop exceeds a certain limit, then you have to reverse the flow, so that the particles that are trapped inside the filter medium can be removed. So, these are essentially all the basic separation processes that are used in chemical industry. Depending on what kind of mixture we have, reaction mixture we have to go for selection of a process. Now, taking the same example of HDA process that we have seen in the previous modules, hydrodealkylation. That process contains total 5 components. The reactor effluent contains 5 components. First is the product benzene, the byproduct diphenyl, toluene, unreacted toluene, hydrogen and methane. Now, when the reactor effluent comes out, it is in vapor phase. So, all components are in vapor phase. So, we have to phase split that. So, phase split becomes the first separation operation. Then, how is phase split obtained? It is by expansion, okay, of the reaction mixture. However, before the reactor effluent is at high temperature, 1800 degrees Fahrenheit, and sorry 1300 degrees Fahrenheit, and then it is at high pressure also, about 500 psi pressure. We first try to recover the heat of that particular stream through different exchangers. That whole topic will be covered in the module of heat integration of the process, and then we go for phase splitting. The high boiling components like benzene, toluene, diphenyl, they condense, hydrogen and methane are left out, and then the separation of the benzene, toluene and diphenyl is achieved through 2 distillation columns. And then for the gaseous mixture, we have to go for purging, so that the methane concentration does not get built up beyond a certain limit, and then part of the gas is recycled and part is purged. So, however, nowadays, since these membrane modules are available for gas separation, okay, you can install another separation process, that is a gas separation process, so that selectively methane is purged and hydrogen is recycled. If you use a general recycle purge stream, then along with methane some hydrogen also gets purged, but by application of a membrane module at the purge stream, you can selectively filter out hydrogen and recycle to the reactor. In the subsequent lectures, we shall see how we can generally design a separation process, making a combination of all these unit operations that we have reviewed in this lecture. And then we shall study mainly the distillation operation. As I told you, for absorption we have a separate module for economic decision making and design of absorption columns. So, that topic is treated in greater detail in that module. Other topics are already covered, the basic principles in the mass transfer courses. So, we shall focus mainly on the distillation operation in the subsequent lectures of this module. We shall see how distillation column sequence is designed, what are the guidelines, what are the quick methods of design of a distillation column, the number of plates, deciding the reflux ratio. So, that will be the content of the coming lectures. In the second lecture, that is immediate next to this, we shall see the general design of separation process, like what the separation processes we have to use and where these should be located in the overall process, and thereafter the distillation operation will be studied in detail.